Hello, I'm Minjung-yu. I'm PhD student in Sungkyukwon University. Today, I'm presenting our paper, Exploratory Retrieval-Augmented Planning for Continuous Embodied Instruction Following. Let me introduce our CSI lab. Our lab, led by Professor Hong Woo, primarily focus on training robust agents that can perform well in various environments and adapt quickly to new environment via reinforcement learning or imitation learning. Firstly, we conduct research on multitask and meta-reinforcement learning, aiming to develop reinforcement learning algorithms that can quickly adapt to new tasks and perform various tasks. And we implement models capable of handling multimodal data, such as images and language, to train agents that operate robustly in diverse new environments. In case where data in the target environment is scarce, we focus on utilizing data from other environments. Also, we conduct research on offline reinforcement learning to achieve good performance even with limited data. Lastly, we are researching skill-based reinforcement learning to train and perform complex and long-horizon tasks. We decompose tasks into round skills, enabling rapid adaptation to unseen tasks with minimal data. I would like to introduce the conference where our paper have been accepted. EURIPS is a conference on your information processing systems, serving as a platform for researchers and industry professionals worldwide to present and share cutting-edge research findings and innovative technologies. Each year, it attracts numerous researchers, scholars, and industry experts from around the globe to discuss and advance various topics related to the latest AI techniques. As one of the most prestigious conferences in the field of general AI, EURIPS provides selected papers and diverse programs to offer important news and insights to experts in the field. From now, I'm presenting our paper, Exploratory Retrieval-Augmented Planning for Continuous Embodied Instruction Following, accepted in EURIPS 2024. First, let me explain embodied AI. Embodied AI is a field of artificial intelligence that runs and solves problems through actions and interaction in the physical world. Typically, it includes activities involving physical agents such as home robots and autonomous vehicles, as well as simulation environments. In these environments, an embodied AI agent requires sequential decision-making to take in user instructions and execute them. Such embodied AI models are tasked with operating in diverse and dynamic environments, requiring open domain adaptability. Additionally, information about the environment is typically conveyed through various modalities such as images, language, or spatial data from sensor input. To address these challenges, there has been active research on leveraging large language models to implement agents that can describe this complex environment in natural language, achieve high performance in open domain, and adapt rapidly. For example, Zero-shot Planner is capable of performing embodied tasks quickly without prior data. And prog prompt adapts to environmental changes through planning based on programming language style inputs. LLM Planner enhances planning by utilizing in-context data and a trial and error approach for decision making. Then I explain the problem definition of my paper. When considering the use of embodied AI agents in real-world scenario, the commands given to these agents can include both temporary instructions and continuous instruction. However, continuous instructions are generally more convenient and efficient for users. For example, with a home robot, a user could command like open the window whenever needed, but typically, it is more convenient for users to preset conditions, such as open the window when the temperature exceeds a certain threshold, or open the window when the indoor air quality becomes poor. In this work, we consider the use of embodied AI agents in real-world scenario and for the first time define the problem of following continuous instructions that must be continuously performed in dynamic environments. We also conduct research to address this problem. Embodied agents must execute multiple instructions within an environment, and these continuous instructions are generally conditional in nature. Therefore, efficient task execution and effective utilization of collected information become critically important. Then I explain the problem of existing research in this context. First, there is inefficiency caused by the sequential execution of multiple instructions. For example, consider these 4 continuous instructions. Existing methods are designed to execute these instructions sequentially, one after the other. Ignoring the relationships or dependencies among multiple instructions and executing them sequentially results in significant inefficiency. Second, environmental information is represented as text to be utilized by LLMs, but this approach is highly unsuitable for managing and using such information effectively. For example, it becomes very challenging to manage redundant information, update outdated information as the environment changes, or even locate the specific pieces of information needed. Moreover, wrong textual information not only degrades the inference performance of LLMs, but also makes it difficult to fully leverage past information. Our proposed ExRAP framework addresses these 2 issues through 2 main approaches. First, it supports integrated execution of multiple instructions. Instead of performing each task one by one in the current environment, the framework efficiently integrates multiple instructions by considering overlapping route and processes, enabling a more streamlined execution. Second, it introduces retrieval-augmented planning based on a knowledge graph. By utilizing a temporal embodied knowledge graph that reflects spatial and temporal dynamics, the framework efficiently manages updated and outdated information. It retrieves only the relevant information needed for the current tasks, improving inference performance. Here is an explanation of the components of our ExRAP framework. First, the environmental context memory manages and stores environmental information using temporal embodied knowledge graph. This component supports information retrieval through a DPL-based model. Then our decision-making process for each time step is conducted in two stages. The first stage is query evaluation. In this stage, we extract the specific instruction from continual instructions that need to be performed at this step. Relevant information is retrieved to determine whether the current instruction should be executed. Here, we employ an LLM and perform a temporal consistency refinement using visual information to help the LLM better understanding the temporal decay of outdated information in a changing environment. This approach encourages the LLM's uncertainty to increase when it relies on outdated information for reasoning, which is particularly effective when using SLMs with weaker reasoning capability for temporal information. The second stage is exploration integrated task planning. This stage involves evaluating the value of executable skills for multiple instructions and selecting the skill to execute based on this assessment. Additionally, the framework incorporates the value of exploration aimed at maintaining the freshness of the knowledge graph. The value of exploration is calculated based on the information gain, and this is integrated into the decision-making process to enable exploration integrated task planning. Here is a detailed explanation of query evaluation. The goal of query evaluation is to select the appropriate execution from a set of conditional instructions, continual instructions that need to be carried out at the current time step. To achieve this, the instruction interpreter first divides each instruction into a query component and an execution component. Then retrieval is performed to determine whether the current conditions are true or false. At this stage, the query evaluator ensures that the uncertainty of the query response increased as the retrieved information becomes older. The temporal consistency refinement improves the performance of the LLM in evaluating queries within dynamic environments by filtering out responses where the LLM fails to account for increased uncertainty despite relying on the outdated information. Through this process, the execution to be performed at the current time step is inferred. Here is an explanation of exploration integrated task planning. Exploration integrated task planning consists of two components, the exploitation planner and the exploration planner. Exploitation planner focuses on selecting the most valuable skill from the available skills based on the execution derived from the prior stages. It aggregates the value of skills for each execution and integrates them to perform comprehensive planning. The primary objective here is to maximize task performance by identifying and executing the skill with the highest value. The exploration planner, on the other hand, aims not just to execute tasks but to maintain up-to-date information about the environment. Since it is impractical to keep all environments current, the planner prioritizes collecting information that is most relevant to the query. To achieve this, it measures the information gain relative to the query when a skill is executed, thereby focusing on the skill that yield the most significant update to the knowledge graph. By combining the value from both planners through a weighted sum, the framework performs exploration integrated task planning, which balance efficient task execution with maintaining the freshness of environmental information. This process is repeated iteratively in the environment. To evaluate ExRAP's effectiveness, we evaluated it in 3 distinct environments: virtual home, Alfred, and color. These settings simulated household management and autonomous driving tasks, respectively. Each environment includes non-stationary elements with varying degree of changes, allowing us to assess ExRAP performance in both stable and highly dynamic scenarios. In our evaluations, ExRAP demonstrated superior performance compared to other LLM-based methods, achieving higher goal success rate and execution effectively. Its strength becomes more evident in high non-stationary scenarios, where it adapts effectively to frequent and complex environmental changes, maintaining robust task performance. Through qualitative analysis, we observed that ExRAP's exploration strategy allows it to cover more larger areas in the environment than other models, making it better suited to handle continuous tasks. Additionally, our evaluation studies showed that features like temporal consistency refinement and exploration integrated planning play key roles in ExRAP high performance. This adaptability is crucial for managing complex, multiple instructions environment effectively. In conclusion, ExRAP introduces a new approach for continuous instruction following by leveraging exploratory retrieval-augmented planning. This framework significantly improves the adaptability and effectiveness of agents in non-stationary environments with continuous instructions, as demonstrated in the virtual home, Alfred, and Kala environment. In the future, we plan to explore more advanced memory mechanism and adaptation technique to further enhance ExRAP's performance in increasingly complex environment.